Hi, everyone. Let's get started. Good afternoon, and welcome to MIT 6S191. This is really incredible to see the turnout this year. This is the fourth year now we're teaching this course, and every single year it just seems to be getting bigger and bigger. 6S191 is a one-week intensive boot camp on everything deep learning. In the past, at this point, I usually try to give you a synopsis about the course and tell you all of the amazing things that you're going to be learning. You'll be gaining fundamentals into deep learning and learning some practical knowledge about how you can implement some of the algorithms of deep learning in your own research and on some cool lab-related software projects. But this year, I figured we could do something a little bit different. And instead of me telling you how great this class is, I figured we could invite someone else from outside the class to do that instead. So let's check this out first.
Hi, everybody, and welcome to MIT 6S191, the official introductory course on deep learning taught here at MIT. Deep learning is revolutionizing so many fields, from robotics to medicine and everything in between. You'll learn the fundamentals of this field and how you can build some of these incredible algorithms. In fact, this entire speech and video are not real, and were created using deep learning and artificial intelligence. And in this class, you'll learn how. It has been an honor to speak with you today, and I hope you enjoy the course.
Right. So, as you can tell, deep learning is an incredibly powerful tool. This was just an example of how we use deep learning to perform voice synthesis and actually emulate someone else's voice, in this case, Barack Obama, and also using video dialogue replacement to actually create that video with the help of Kenny AI. And of course, as you're watching this video, you might raise some ethical concerns, which we're also very concerned about, and we'll actually talk about some of those later on in the class as well. But let's start by taking a step back and actually introducing some of these terms that we've talked about so far. Now let's start with the word intelligence. I like to define intelligence as the ability to process information to inform future decisions. Now, the field of artificial intelligence is simply the field which focuses on building algorithms, in this case, artificial algorithms, that can do this as well, process information to inform future decisions. Now, machine learning is just a subset of artificial intelligence, specifically that focuses on actually teaching an algorithm how to do this without being explicitly programmed to do the task at hand. Now, deep learning is just a subset of machine learning, which takes this idea even a step further and says, how can we automatically extract the useful pieces of information needed to inform those future predictions or make a decision? And that's what this class is all about. Teaching algorithms how to learn a task directly from raw data. And we want to provide you with a solid foundation of how you can understand, or how to understand these algorithms under the hood, but also provide you with the practical knowledge and practical skills to implement state-of-the-art deep learning algorithms in TensorFlow, which is a very popular deep learning toolbox. Now, we have an amazing set of lectures lined up for you this year, including today, which will cover neural networks and deep sequential modeling. Tomorrow, we'll talk about computer vision, and also a little bit about generative modeling, which is how we can generate new data. And finally, we'll talk about deep reinforcement learning and touch on some of the limitations and new frontiers of where this field might be going and how research might be heading in the next couple of years. We'll spend the final 2 days hearing about some of the guest lectures from top industry researchers on some really cool and exciting projects. Every year, these happen to be really, really exciting talks, so we really encourage you to come, especially for those talks. The class will conclude with some final project presentations, which we'll talk about in a little bit, and also some awards and a quick award ceremony to celebrate all of your hard work. Also, I should mention that after each day of lectures, so after today, we have 2 lectures, and after each day of lectures, we'll have a software lab, which tries to focus and build upon all of the things that you've learned in that day. So you'll get the foundations during the lectures, and you'll get the practical knowledge during the software lab. So the 2 are kind of jointly coupled in that sense. For those of you taking this class for credit, you have a couple different options to fulfill your credit requirement. First is a project proposal. First you can propose a project in optionally groups of 2, 3, or 4 people. And in these groups, you'll work to develop a cool new deep learning idea. And we realized that 1 week, which is the span of this course, is an extremely short amount of time to really not only think of an idea, but move that idea past the planning stage and try to implement something. So we're not going to be judging you on your results towards this idea, but rather just the novelty of the idea itself. On Friday, each of these 3 teams will give a 3-minute presentation on that idea, and the awards will be announced for the top winners, judged by a panel of judges. The second option, in my opinion, is a bit more boring, but we like to give this option for people that don't like to give presentations. So in this option, if you don't want to work in a group or you don't want to give a presentation, you can write a 1-page paper review of a recent deep learning paper or any paper of your choice, and this will be due on the last day of class as well. Also, I should mention that for the project presentations, we give out all of these cool prizes, especially these 3 NVIDIA GPUs, which are really crucial for doing any sort of deep learning on your own. So we definitely encourage everyone to enter this competition and have a chance to win these GPUs and these other cool prizes like Google Home and the SSD cards as well. Also, for each of the labs, the 3 labs will have corresponding prizes. So instructions to actually enter those respective competitions will be within the labs themselves, and you can enter to win these different prizes depending on the different lab. Please post to Piazza if you have questions. Check out the course website for slides. Today's slides are already up. There was a bug in the website. We fixed that now, so today's slides are up now. Digital recordings of each of these lectures will be up a few days after each class. This course has an incredible team of TAs that you can reach out to if you have any questions, especially during the software labs. They can help you answer any questions that you might have. And finally, we really want to give a huge thank to all of our sponsors who, without their help and support, this class would have not been possible. Okay, so now with all of that administrative stuff out of the way, let's start with the fun stuff that we're all here for. Let's start actually by asking ourselves a question. Why do we care about deep learning? Well, why do you all care about deep learning, and all of you came to this classroom today? And why specifically do you care about deep learning now? Well, to answer that question, we actually have to go back and understand traditional machine learning at its core first. Now, traditional machine learning algorithms typically try to define a set of rules or features in the data, and these are usually hand-engineered. And because they're hand-engineered, they often tend to be brittle in practice. So let's take a concrete example. If you wanted to perform facial detection, how might you go about doing that? Well, first, you might say, to classify a face, the first thing I'm going to do is I'm going to try and classify or recognize if I see a mouth in the image, eyes, ears, a nose. If I see all of those things, then maybe I can say that there's a face in that image. But then the question is, okay, but how do I recognize each of those sub-things? Like, how do I recognize an eye? How do I recognize a mouth? And then you have to decompose that into, okay, to recognize a mouth, I maybe have to recognize these pairs of lines, oriented lines in a certain direction, certain orientation. And then it keeps getting more complicated. And each of these steps, you kind of have to define a set of features that you're looking for in the image. Now, the key idea of deep learning is that you need to learn these features just from raw data. So what you're going to do is you're going to just take a bunch of images of faces, and then the deep learning algorithm is going to develop some hierarchical representation of first detecting lines and edges in the image, using these lines and edges to detect corners and eyes and mid-level features like eyes, noses, mouths, ears, then composing these together to detect higher-level features like maybe jaw lines, side of the face, etc., which then can be used to detect the final face structure. And actually, the fundamental building blocks of deep learning have existed for decades. And their underlying algorithms for training these models have also existed for many years. So why are we studying this now? Well, for one, data has become much more pervasive. We're living in the age of big data, and these algorithms are hungry for huge amounts of data to succeed. Secondly, these algorithms are massively parallelizable, which means that they can benefit tremendously from modern GPU architectures and hardware acceleration that simply did not exist when these algorithms were developed. And finally, due to open source toolboxes like TensorFlow, which you'll get experience with in this class, building and deploying these models has become extremely streamlined, so much so that we can condense all of this material down into 1 week. So let's start with the fundamental building block of a neural network, which is a single neuron, or what's also called a perceptron. The idea of a perceptron, or a single neuron, is very basic, and I'll try and keep it as simple as possible, and then we'll try and work our way up from there. Let's start by talking about the forward propagation of information through a neuron. We define a set of inputs to that neuron as x1 through xm. And each of these inputs have a corresponding weight, w1 through wm. Now what we can do is, with each of these inputs and each of these weights, we can multiply them correspondingly together and take a sum of all of them. Then we take this single number, that summation, and we pass it through what's called a nonlinear activation function. And that produces our final output, y. Now, this is actually not entirely correct. We also have what's called a bias term in this neuron, which you can see here in green. So the bias term, the purpose of the bias term is really to allow you to shift your activation function to the left and to the right, regardless of your inputs. Right? So you can notice that the bias term is not affected by the x's. It's just a bias associated to that input. Now, on the right side, you can see this diagram illustrated mathematically as a single equation. And we can actually rewrite this as a linear, using linear algebra in terms of vectors and dot products. So instead of having a summation over all of the x's, I'm going to collapse my x into a vector, capital X, which is now just a list or a vector of numbers, a vector of inputs, I should say. And you also have a vector of weights, capital W. To compute the output of a single perceptron, all you have to do is take the dot product of X and W, which represents that element-wise multiplication and summation, and then apply that nonlinearity, which here is denoted as G. So now you might be wondering, what is this nonlinear activation function? I've mentioned it a couple times, but I haven't really told you precisely what it is. Now, one common example of this activation function is what's called a sigmoid function. And you can see an example of a sigmoid function here on the bottom right. One thing to note is that this function takes any real number as input on the x-axis, and it transforms that real number into a scalar output between 0 and 1. It's a bounded output between 0 and 1. So one very common use case of the sigmoid function is when you're dealing with probabilities, because probabilities have to also be bounded between 0 and 1. So sigmoids are really useful when you want to output a single number and represent that number as a probability distribution. In fact, there are many common types of nonlinear activation functions, not just the sigmoid, but many others that you can use in neural networks, and here are some common ones. And throughout this presentation, you'll find these TensorFlow icons, like you can see on the bottom right, or sorry, all across the bottom here. And these are just to illustrate how one could use each of these topics in a practical setting. You'll see these kind of scattered in throughout the slides. No need to really take furious notes at these code blocks. Like I said, all of the slides are published online, so especially during your labs, if you want to refer back to any of the slides, you can always do that from the online lecture notes. Now, why do we care about activation functions? The point of an activation function is to introduce nonlinearities into the data. And this is actually really important in real life, because in real life, almost all of our data is nonlinear. And here's a concrete example. If I told you to separate the green points from the red points using a linear function, could you do that? I don't think so, right? So you'd get something like this. Well, you could do it. You wouldn't do a very good job at it. And no matter how deep or how large your network is, if you're using a linear activation function, you're just composing lines on top of lines, and you're going to get another line, right? So this is the best you'll be able to do with a linear activation function. On the other hand, nonlinearities allow you to approximate arbitrarily complex functions by kind of introducing these nonlinearities into your decision boundary. And this is what makes neural networks extremely powerful. Let's understand this with a simple example, and let's go back to this picture that we had before. Imagine I give you a trained network with weights W on the top right. So W here is 3 and minus 2. And the network only has two inputs, x1 and x2. If we want to get the output, it's simply the same story as we had before. We multiply our inputs by those weights, we take the sum, and pass it through a nonlinearity. But let's take a look at what's inside of that nonlinearity before we apply it. So what we get is, when we take this dot product of x1 times 3, x2 times minus 2, and we add that to 1, that's simply a 2D line. So we can plot that. If we set that equal to 0, for example, that's a 2D line, and it looks like this. So on the x-axis is x1, on the y-axis is x2, and we're just illustrating when this line equals 0. So anywhere on this line is where x1 and x2 correspond to a value of 0. Now, if I feed in a new input, either a test example, a training example, or whatever, and that input is with this coordinates, it has these coordinates, -1 and 2. So it has a value of x1 of -1, value of x2 of 2. I can see visually where this lies with respect to that line. And in fact, this idea can be generalized a little bit more. If we compute that line, we get -6, right? So inside that, before we apply the nonlinearity, we get -6. When we apply a sigmoid nonlinearity, because sigmoid collapses everything between 0 and 1, anything greater than 0 is going to be above 0.5. Anything below 0 is going to be less than 0.5. So because -6 is less than 0, we're going to have a very low output. This 0.002. And we can actually generalize this idea. For the entire feature space, let's call it, for any point on this plot, I can tell you if it lies on the left side of the line, that means that before we apply the nonlinearity, the z, or the state of that neuron, will be negative, less than 0. After applying that nonlinearity, the sigmoid will give it a probability of less than 0.5. And on the right side, if it falls on the right side of the line, it's the opposite story. If it falls right on the line, it means that z equals 0 exactly, and the probability equals 0.5. Now, actually, before I move on, this is a great example of actually visualizing and understanding what's going on inside of a neural network. The reason why it's hard to do this with deep neural networks is because you usually don't have only two inputs, and you usually don't have only two weights as well. So as you scale up your problem, this is a simple two-dimensional problem, but as you scale up the size of your network, you could be dealing with hundreds or thousands or millions of parameters and million-dimensional spaces. And then visualizing these type of plots becomes extremely difficult, and it's not practical in practice. So this is one of the challenges that we face when we're training with neural networks and really understanding their internals. But we'll talk about how we can actually tackle some of those challenges in later lectures as well. Okay, so now that we have that idea of a perceptron, a single neuron, let's start by building up neural networks now. How we can use that perceptron to create full neural networks and seeing how all of this story comes together. Let's revisit this previous diagram of the perceptron. If there are only a few things you remember from this class, try to take away this. So how a perceptron works, just keep remembering this. I'm going to keep drilling it in. You take your inputs, you apply a dot product with your weights, and you apply a nonlinearity. It's that simple. Oh, sorry, I missed a step. You have to dot product with your weights, add a bias, and apply your nonlinearity. So 3 steps. Now let's simplify this diagram a little bit. I'm going to remove the bias just for simplicity. I'm going to remove all of the weight labels. So now you can assume that every line has a weight associated to it. And let's see, so I'm going to note z, that z is the output of that dot product. So that's the element-wise multiplication of our inputs with our weights. And that's what gets fed into our activation function. So our final output y is just our activation function applied on z. If we want to define a multi-output neural network, we simply can just add another one of these perceptrons to this picture. Now we have two outputs. One is a normal perceptron, which is y1, and y2 is just another normal perceptron. The same idea as before, they all connect to the previous layer with a different set of weights. And because all inputs are densely connected to all of the outputs, these type of layers are often called dense layers. And let's take an example of how one might actually go from this nice illustration, which is very conceptual and nice and simple, to how you could actually implement one of these dense layers from scratch by yourselves using TensorFlow. So what we can do is start off by first defining our two weights. So we have our actual weight vector, which is w, and we also have our bias vector, right? Both of these parameters are governed by the output space. So depending on how many neurons you have in that output layer, that will govern the size of each of those weight and bias vectors. And what we can do then is simply define that forward propagation of information. So here I'm showing you this through the call function in TensorFlow. Don't get too caught up on the details of the code. Again, you'll get really a walkthrough of this code inside of the labs today, but I want to just show you some high-level understanding of how you could actually take what you're learning and apply the TensorFlow implementations to it. Inside the call function, it's the same idea again. You can compute z, which is the state. It's that multiplication of your inputs with the weights. You add the bias, right? So that's right there. And once you have z, you just pass it through your sigmoid, and that's your output for that layer. Now, TensorFlow is great because it's already implemented a lot of these layers for us, so we don't have to do what I just showed you from scratch. And in fact, to implement a layer like this with two outputs, or a multi-output perceptron layer with two outputs, we can simply call this tf.keras layers dense with units equal to 2 to indicate that we have two outputs on this layer. And there was a whole bunch of other parameters that you could input here, such as the activation function, as well as many other things to customize how this layer behaves in practice. So now let's take a look at a single layered neural network. So this is taking it one step beyond what we've just seen. This is where we have now a single hidden layer that feeds into a single output layer. And I'm calling this a hidden layer because unlike our inputs and our outputs, the states of the hidden layer are not directly enforced, or they're not directly observable. We can probe inside the network and see them, but we don't actually enforce what they are. These are learned, as opposed to the inputs, which are provided by us. Now, since we have a transformation between the inputs and the hidden layer and the output layer, each of those two transformations will have their own weight matrices, which here I call W1 and W2. So this corresponds to the first layer and the second layer. If we look at a single unit inside of that hidden layer, take, for example, Z2, I'm showing here, that's just a single perceptron, like we talked about before. It's taking a weighted sum of all of those inputs that feed into it, and it applies a nonlinearity and feeds it onto the next layer. Same story as before. This picture actually looks a little bit messy, so what I want to do is actually clean things up a little bit for you. And I'm going to replace all of those lines with just this symbolic representation, and we'll just use this from now on in the future to denote dense layers or fully connected layers between an input and an output, or between an input and a hidden layer. And again, if we wanted to implement this in TensorFlow, the idea is pretty simple. We can just define two of these dense layers. The first one, our hidden layer with n outputs, and the second one, our output layer with two outputs. We can like join them together, aggregate them together into this wrapper, which is called a TF sequential model. And sequential models are just this idea of composing neural networks using a sequence of layers. So whenever you have a sequential message passing system or sequentially processing information throughout the network, you can use sequential models and just define your layers as a sequence, and it's very nice to allow information to propagate through that model. Now, if we want to create a deep neural network, the idea is basically the same thing, except You just keep stacking on more of these layers and to create more of a hierarchical model. Ones where the final output is computed by going deeper and deeper into this representation. And the code looks pretty similar again. So again, we have this TF sequential model, and inside that model, we just have a list of all of the layers that we want to use, and they're just stacked on top of each other. Okay, so this is awesome. So hopefully now you have an understanding of not only what a single neuron is, but how you can compose neurons together and actually build complex hierarchical models with neural networks. Now let's take a look at how you can apply these neural networks into a very real and applied setting to solve some problem and actually train them to accomplish some task. Here's a problem that I believe any AI system should be able to solve for all of you, and probably one that you care a lot about. Will I pass this class? To do this, let's start with a very simple two-input model. One feature or one input we're going to define is how many lectures you attend during this class. And the second one is the number of hours that you spend on your final project. I should say that the minimum number of hours you can spend on your final project is 50 hours. No, I'm just joking. Okay, so let's take all of the data from previous years and plot it on this feature space like we looked at before. Green points are students that have passed the class in the past, and red points are people that have failed. We can plot all of this data onto this two-dimensional grid like this, and we can also plot you. So here you are. You've attended 4 lectures, and you've only spent 5 hours on your final exam, or on your final project. And the question is, are you going to pass the class? Given everyone around you and how they've done in the past, how are you going to do? So let's do it. We have 2 inputs. We have a single hidden layer neural network. We have 3 hidden units in that hidden layer. And we'll see that the final output probability, when we feed in those 2 inputs of 4 and 5, is predicted to be 0.1, or 10%. The probability of you passing this class is 10%. That's not great news. The actual prediction was 1, so you did pass the class. Now, does anyone have an idea of why the network was so wrong in this case?
Maybe the weights weren't right?
Yeah, exactly. So we never told this network anything. The weights are wrong. We've just initialized the weights. In fact, it has no idea what it means to pass a class. It has no idea of what each of these inputs mean, how many lectures you've attended, how many hours you've spent on your final project. It's just seeing some random numbers. It has no concept of how other people in the class have done so far. So what we have to do to this network first is train it, and we have to teach it how to perform this task. Until we teach it, it's just like a baby that doesn't know anything. So it's just entered the world. It has no concepts or no idea of how to solve this task, and we have to teach it that. Now, how do we do that? The idea here is that first we have to tell the network when it's wrong. So we have to quantify what's called its loss or its error. And to do that, we actually just take our prediction, or what the network predicts, and we compare it to what the true answer was. If there's a big discrepancy between the prediction and the true answer, we can tell the network, hey, you made a big mistake, right? So there's a big error, it's a big loss, and you should try and fix your answer to move closer towards the true answer, which it should be, okay? Now, you can imagine if you don't have just one student, but now you have many students, the total loss, let's call it here the empirical risk or the objective function, it has many different names, it's just the average of all of those individual losses. So the individual loss is a loss that takes as input your prediction and your actual. That's telling you how wrong that single example is. And then the total loss, is just the average of all of those individual student losses. So if we look at the problem of binary classification, which is the case that we're actually caring about in this example, so we're asking a question, will I pass the class, yes or no, binary classification? We can use what is called as the softmax cross-entropy loss. And for those of you who aren't familiar with cross-entropy, this was actually a formulation introduced by Claude Shannon here at MIT during his master's thesis as well. And this was about 50 years ago. It's still being used very prevalently today. And the idea is it just, again, compares how different these two distributions are. So you have a distribution of how likely you think the student is going to pass, and you have the true distribution of if the student passed or not. You can compare the difference between those two distributions, and that tells you the loss that the network incurs on that example. Now let's assume that instead of a classification problem, we have a regression problem, where instead of predicting if you're going to pass or fail the class, you want to predict the final grade that you're going to get. So now it's not a yes-no answer problem anymore, but instead it's a what's the grade I'm going to get? What's the number? So it's a full range of numbers that are possible now. And now we might want to use a different type of loss for this different type of problem. And in this case, we can do what's called a mean squared error loss. So we take the actual prediction, we take we take the prediction of the network, we take the actual true final grade that the student got, we subtract them, we take their squared error, and we say that that's the mean squared error, that's the loss that the network should try to optimize and try to minimize. So now that we have all this information with the loss function and how to actually quantify the error of the neural network, let's take this and understand how to train our model to actually find those weights that it needs to use for its prediction. So W is what we want to find out. W is the set of weights, and we want to find the optimal set of weights that tries to minimize this total loss over our entire test set. So our test set is this example data set that we want to evaluate our model on. So in the class example, the test set is you. So you want to understand how likely you are to pass this class. You're the test set. Now what this means is that we want to find the W's that minimize that total loss function, which we call as the objective function J of W. Now, remember that W is just a aggregation or a collection of all of the individual W's from all of your weights. So here, this is just a way for me to express this in a clean notation, but W is a whole set of numbers. It's not just a single number. And you want to find all of the W's. You want to find the value of each of those weights such that you can minimize this entire loss function. It's a very complicated problem. And remember that our loss function is just a simple function in terms of those weights. So if we plot, in the case again of a two-dimensional weight problem, so one of the weights is on the x-axis, one of the weights is on this axis, and on the z-axis we have the loss. So for any value of W, we can see what the loss would be at that point. Now, what do we want to do? We want to find the place on this landscape. What are the values of W that we get the minimum loss? Okay, so what we can do is we can just pick a random W, pick a random place on this landscape to start with. And from this random place, let's try to understand how the landscape is changing. What's the slope of the landscape? We can take the gradient of the loss with respect to each of these weights to understand the direction of maximum ascent. Okay, that's what the gradient tells us. Now that we know which way is up, we can take a step in the direction that's down. So we know which way is up, we reverse the sign, so now we start heading downhill, and we can move towards that lowest point. Now we just keep repeating this process over and over again until we've converged to a local minimum. Now we can summarize this algorithm, which is known as gradient descent, because you're taking a gradient and you're descending down that landscape by starting to initialize our weights randomly. We compute the gradient, dj, with respect to all of our weights. Then we update our weights in the opposite direction of that gradient and take a small step, which we call here eta, of that gradient. And this is referred to as the learning rate. And we'll talk a little bit more about that later, but eta is just a scalar number that determines how much of a step you want to take at each iteration. How strongly or aggressively do you want to step towards that gradient? In code, the picture looks very similar. So to implement gradient descent is just a few lines of code, just like the pseudocode. You can initialize your weights randomly in the first line. You can compute your loss with respect to those gradients and with respect to those predictions and your data. Given that gradient, you just update your weights in the opposite direction of that vector, right? Now the magic line here is actually how do you compute that gradient? And that's something I haven't told you yet, and that's something that's not easy at all. So the question is, given a loss and given all of our weights in our network, how do we know which way is good, which way is a good place to move, given all of this information? And I never told you about that, but that's a process called backpropagation. And let's talk about a very simple example of how we can actually derive backpropagation using elementary calculus. So we'll start with a very simple network with only one hidden neuron and one output. This is probably the simplest neural network that you can create. You can't really get smaller than this. Computing the gradient of our loss with respect to W2 here, which is that second weight between the hidden state and our output, can tell us how much a small change in W2 will impact our loss. So that's what the gradient tells us, right? If we change W2 in a like a very minor manner, how does our loss change? Does it go up or down? How does it change? And by how much, really? So that's the gradient that we care about, the gradient of our loss with respect to W2. Now, to evaluate this, we can just apply the chain rule in calculus. So we can split this up into the gradient of our loss with respect to our output, y, multiplied by the gradient of our output, y, with respect to W2. Now, if we want to repeat this process for a different weight in the neural network, let's say now W1, not W2. Now we replace W1 on both sides. We also apply the chain rule, but now you're going to notice that the gradient of y with respect to W1 is also not directly computable. We have to apply the chain rule again to evaluate this. So let's apply the chain rule again. We can break that second term up with respect to now the state z, okay? And using that, we can kind of backpropagate all of these gradients from the output all the way back to the input. And that allows our error signal to really propagate from output to input and allows these gradients to be computed in practice. Now, a lot of this is not really important, or excuse me, it's not as crucial that you understand the nitty-gritty math here, because in a lot of popular deep learning frameworks, we have what's called automatic differentiation, which does all of this backpropagation for you under the hood, and you never even see it, which is incredible. It makes training neural networks so much easier. You don't have to implement backpropagation anymore. But it's still important to understand how these work at the foundation, which is why we're going through it now. Okay, obviously, then you repeat this for every single weight in the network. Here we showed it for just W1 and W2, which is every single weight in this network. But if you have more, you can just repeat it again. Keep applying the chain rule from output to input to compute this. Okay, and that's the backprop algorithm. In theory, very simple. It's just an application of the chain rule in essence. But now let's touch on some of the insights from training and how you can use the backprop algorithm to train these networks in practice. Optimization of neural networks is incredibly tough in practice. So it's not as simple as the picture I showed you on the colorful one on the previous slide. Here's an illustration from a paper that came out about 2 or 3 years ago now, where the authors tried to visualize the landscape of a neural network with millions of parameters, but they collapsed that down onto just 2-dimensional space so that we can visualize it. And you can see that the landscape is incredibly complex. It's not easy. There are many local minima where the gradient descent algorithm could get stuck into. And applying gradient descent in practice in these type of environments, which is very standard in neural networks, can be a huge challenge. Now, recall the update equation that we defined previously with gradient descent. This is that same equation. We're going to update our weights in the opposite direction of our gradient. I didn't talk too much about this parameter eta. I pointed it out before. This is the learning rate. It determines how much of a step we should take in the direction of that gradient. And in practice, setting this learning rate can have a huge impact in performance. So if you set that learning rate too small, that means that you're not really trusting your gradient on each step. So if eta is super tiny, that means that on each step, you're only going to move a little bit in the opposite direction of your gradient, just in little small increments. And what can happen then is you can get stuck in these local minima because you're not being as aggressive as you should be to escape them. Now, if you set the learning rate too large, you can actually overshoot completely and diverge, which is even more undesirable. So setting the learning rate can be very challenging in practice. You want to pick a learning rate that's large enough such that you avoid the local minima, but small enough such that you still converge in practice. Now, the question that you're all probably asking is, how do we set the learning rate then? Well, one option is that you can just try a bunch of learning rates and see what works best. Another option is to do something a little bit more clever and see if we can try to have an adaptive learning rate that changes with respect to our lost landscape. Maybe it changes with respect to how fast the learning is happening, or a range of other ideas within the network optimization scheme itself. This means that the learning rate is no longer fixed, but it can now increase or decrease throughout training. So as training progresses, your learning rate may speed up. You may take more aggressive steps. You may take smaller steps as you get closer to the local minima so that you really converge on that point. And there are many options here of how you might want to design this adaptive algorithm. And this has been a huge or a widely studied field in optimization theory for machine learning and deep learning. And there have been many published papers and implementations within TensorFlow on these different types of adaptive learning rate algorithms. So SGD is just that vanilla gradient descent that I showed you before. That's the first one. All of the others are all adaptive learning rates, which means that they change their learning rate during training itself. So they can increase or decrease depending on how the optimization is going. And during your labs, we really encourage you again to try out some of these different optimization schemes, see what works, what doesn't work. A lot of it is problem dependent. There are some heuristics that you can get, but we want you to really gain those heuristics yourselves through the course of the labs. It's part of building character. Okay, so let's put this all together. From the beginning, we can define our model, which is defined as this sequential wrapper. Inside of this sequential wrapper, we have all of our layers. All of these layers are composed of perceptrons, or single neurons, which we saw earlier. The second line defines our optimizer, which we saw in the previous slide. This can be SGD. It can also be any of those adaptive learning rates that we saw before. Now, what we want to do is, during our training loop, it's the same story as before. Nothing's changing here. We forward pass all of our inputs through that model. We get our predictions. Using those predictions, we can evaluate them and compute our loss. Our loss tells us how wrong our network was on that iteration. It also tells us how we can compute the gradients and how we can change all of the weights in the network to improve in the future. And then the final line there takes those gradients and actually allows our optimizer to update the weights and the trainable variables such that on the next iteration, they do a little bit better. And over time, if you keep looping, this will converge, and hopefully you should fit your data. Now, I want to continue to talk about some tips for training these networks in practice and focus on a very powerful idea of batching your data into mini batches. So to do this, let's revisit the gradient descent algorithm. This gradient is actually very computationally expensive to compute in practice. So using the backprop algorithm is a very expensive idea in practice. So what we want to do is actually not compute this over all of the data points, but actually compute it over just a single data point in the data set. In most real-life applications, it's not actually feasible to compute on your entire data set at every iteration. It's just too much data. So instead, we pick a single point randomly. We compute our gradient with respect to that point, and then on the next iteration, we pick a different point, and we can get a rough estimate of our gradient at each step. Right, so instead of using all of our data, now we just pick a single point I. We compute our gradient with respect to that single point I. And what's a middle ground here? So the downside of using a single point is that it's going to be very noisy. The downside of using all of the points is that it's too computationally expensive. Is there some middle ground that we can have in between? So that middle ground is actually just very simple. Instead of taking one point and instead of taking all of the points, let's take a mini batch of points. So maybe something on the order of 10, 20, 30, 100 maybe, depending on how rough or accurate you want that approximation of your gradient to be, and how much you want to trade off speed and computational efficiency. Now, the true gradient is just obtained by averaging the gradient from each of those b points. So b is the size of your batch in this case. Now, since b is normally not that large, like I said, maybe on the order of tens to hundreds, this is much faster to compute than full gradient descent and much more accurate than stochastic gradient descent because it's using more than one point, more than one estimate. Now, this increase in gradient accuracy estimation actually allows us to converge to our target much quicker because it means that our gradients are more accurate in practice. It also means that we can increase our learning rate and trust each update more. So if we're very noisy in our gradient estimation, we probably want to lower our learning rate a little more so we don't fully step in the wrong direction if we're not totally confident with that gradient. If we have a larger batch of data to estimate our gradients with, we can trust that learning rate a little more, increase it so that it steps more aggressively in that direction. What this means also is that we can now massively parallelize this computation because we can split up batches on multiple GPUs or multiple computers even to achieve even more significant speedups with this training process. Now, the last topic I want to address is that of overfitting. And this is also known as the problem of generalization in machine learning. And it's actually not unique to just deep learning, but is a fundamental problem of all of machine learning. Now, ideally, in machine learning, we want a model that will approximate or estimate our data or accurately describes our data. Let's say it like that. Said differently, we want to build models that can learn representations from our training data that's still generalized to unseen test data. Now, assume that you want to build a line that best describes these points you can see on the screen. Underfitting describes if our model does not describe the state of complexity of this problem, or if we can't really capture the true complexity of this problem. While overfitting on the right starts to memorize certain aspects of our training data, and this is also not desirable. We want the middle ground, which ideally we end up with a model in the middle that is not too complex to memorize all of our training data, but also one that will continue to generalize when it sees new data. So to address this problem of regularization in neural networks specifically, let's talk about a technique of regularization, which is another way that we can deal with this. And what this is doing is it's trying to discourage complex information from being learned. So we want to eliminate the model from actually learning to memorize the training data. We don't want it to learn like very specific pinpoints of the training data that don't generalize well to test data. Now, as we've seen before, this is actually crucial for our models to be able to generalize to our test data. So this is very important. The most popular regularization technique in deep learning is this very basic idea of dropout. Now, the idea of dropout is, well, actually, let's start with by revisiting this picture of a neural network that we had introduced previously. In dropout, during training, we randomly set some of these activations of the hidden neurons to 0 with some probability. So let's say our probability is 0.5. We're randomly going to set the activations to 0.5 with a probability of 0.5 to some of our hidden neurons to 0. The idea is extremely powerful because it allows the network to lower its capacity. It also makes it such that the network can't build these memorization channels through the network where it tries to just remember the data, because on every iteration, 50% of that data is going to be, or 50% of that memorization or memory is going to be wiped out. So it's going to be forced to not only generalize better, but it's going to be forced to have multiple channels through the network and build a more robust representation of its prediction. Now, we just repeat this on every iteration. So on the first iteration, we dropped out 150% of the nodes. On the next iteration, we can drop out a different randomly sampled 50%, which may include some of the previously sampled nodes as well. And this will allow the network to generalize better to new test data. The second regularization technique that we'll talk about is the notion of early stopping. So what I want to do here is just talk about two lines. So during training, which is the x-axis here, we have two lines. The y-axis is our loss curve. The first line is our training loss. So that's the green line. The green line tells us how our training data, how well our model is fitting to our training data. We expect this to be lower than the second line, which is our testing data. So usually we expect to be doing better on our training data than our testing data. As we train, and as this line moves forward into the future, both of these lines should kind of decrease, go down, because we're optimizing the network, we're improving its performance. Eventually, though, there becomes a point where the training data starts to diverge from the testing data. Now, what happens is that the training data should always continue to fit, or the model should always continue to fit the training data because it's still seeing all of the training data. It's not being penalized from that, except for maybe through dropout or other means. But the testing data, it's not seeing. So at some point, the network is going to start to do better on its training data than its testing data. And what this means is basically that the network is starting to memorize some of the training data. And that's what you don't want. So what we can do is we can perform early stopping, or we can identify this point, this inflection point, where the test data starts to increase and diverge from the training data, so we can stop the network early and make sure that our test accuracy is as minimum as possible. And of course, if we actually look at on the side of this line, if we look at on the left side, that's where our model is underfit. So we haven't reached the true capacity of our model yet. So we'd want to keep training if we didn't stop yet, if we did stop already. And on the right side is where we've overfit, where we've passed that early stopping point, and we need to, basically we've started to memorize some of our training data, and that's when we've gone too far. I'll conclude this lecture by just summarizing 3 main points that we've covered so far. First, we've learned about the fundamentals of neural networks, which is a single neuron, or a perceptron. We've learned about stacking and composing these perceptrons together to form complex hierarchical representations, and how we can mathematically optimize these networks using a technique called backpropagation, using their loss. And finally, we addressed the practical side of training these models, such as mini-batching, regularization, and adaptive learning rates as well. With that, I'll finish up. I can take a couple questions, and then we'll move on to Ava's lecture on deep sequential modeling. I'll take maybe a couple questions if there are any now. Thank you. Thanks.